quantum Hall effect in graphene is quite different from that in a two-dimensional electron gas, and it's quite an interesting example to consider because the electron spectrum of graphene resembles those of relativistic particles, right? So in the relativistic particles, you have this particle-antiparticle as a function of momentum. The behavior is like that: mc squared plus h bar ck squared at magnetic field equals 0. For relativistic particles in non-zero magnetic field, the spectrum becomes quantized. So it's a function of the index of Landau levels, and it has the following form. So there is this mc squared term is the same, plus then the quantized part, which is 2n h bar eb c squared. This one is at b non-equals 0. The derivation is quite involving, and basically consider the Dirac equation in the magnetic field. So in graphene, the rest mass is 0. Then we use this replacement, so the c becomes a Fermi velocity, and the spectrum then becomes, so for graphene, it then also has these plus and minus sides, equals plus and minus Vf times the square root of 2n h bar Eb. And there's several things to note. The first one is that there is at n equals 0, so when you have a zeroth Landau level, so index equals 0, the energy is also equals 0. And that's quite different, that's very different from the two-dimensional electron gas, where you have n plus 1/2 bit because of the simple harmonic oscillation problem. So it's non-zero energy for zeroth Landau level. In graphene, the zeroth Landau level has a 0 energy. Then the second one is that energy of the Landau level is proportional to the square root of b in graphene. And in the 2deg, it's proportional to b. That's in two-dimensional electron gas. And the other one is that energy is also, the energy of Landau level is proportional to the square root of the Landau level index. And in two-dimensional electron gas, it's proportional just to the Landau level index. Then the last bit is that the degeneracy is different. Degeneracy is also different, because in graphene you have 2 spins and 2 valleys. So it's a 4-fold degenerate. Now we can write down this in terms of the degeneracy. So the filling factor is carrier density times h over Eb. And the Landau level, so at n equals 0, you will have a 4-fold degenerate at 0th Landau level. And it's centered at E equals 0. And that means also ns equals 0. So the carrier density is 0. And it has to be separated by the filling factors of plus minus 2 in order for it to be symmetric. So we can draw this on the energy scale. This will be our we use G, right? Density of states, and this is, let's use this one to be 0. So there will be the energy level, so the 0th Landau level, 0th Landau level, and then we'll have some other Landau levels as well. So the first, second, minus first, minus second, and so on. But when you draw them on the carrier density scale, so using this NS, the 0th Landau level would actually be separated by these plus minus 2 degeneracies. So if we have this is our filling factors, which is kind of proportional to the density of states, to carrier density. And this is, for example, rho xy, just to see the quantization. Better to use sigma xy because that's non-equidistant. So around the filling factors plus minus 2, you will have the plateaus in the sigma xy, and these plateaus will be 1/2 of 4e square over h. That's a general unit because you have fourfold degeneracy, so it's 4e square over h, and it will be half integer basically. In this case, you will have minus 1/2 4e square over h for this state. Then the next filling factor will be minus 6 and plus 6, where you will have again these plateaus, and they will then appear at 3/2 of this 4e square over h. This will be minus 3/2 of 4e square over h, and so on. So the quantum Hall effect in graphene is half integer in units of conductance quantum of fourfold degenerate electrons in graphene. And the sequence of these quantum Hall plateaus will be centered at the filling factors, which are again separated by 4 because of degeneracy. It will have a sequence like minus 14, for example, minus 10, minus 6, minus 2, 2, 6, 10, 14, and so on. So the quantization again is shifted by 1/2, as I said. Then you can write it down as so the quantization then would be G degeneracy of a spin, degeneracy of the valley, so that's 2, times e square over h, then times n plus 1/2. And this half integer part, so the presence of 1/2 in the quantization, actually comes from the Berry phase. Berry phase of pi in graphene. We discuss this and other issues related to topology later.